Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Zozin. Let's make a little bit of announcement and officially start the stream as usual. So we're gonna do a red circle live on Twitch. And what are we doing today on Twitch at .television website? So today I decided to do a relatively simple, maybe not that simple, but an interesting exercise. Today I decided to implement a JIT compiler for Brainf, right? So that's what we're going to be doing today. I'm going to give the link to where we're doing all of that, twitch.tv/Toding, and I'm going to ping everyone who's interested in being pinged. And there we go, the stream has officially started. So this exercise was suggested by a good friend of mine, Bitstream, all right? So you can actually check out his profile on GitHub. So he's an inspiring game developer. So one of the games he released recently is this one. So you may actually want to check it out. So this is the exercise that he suggested, and I thought that's a very cool exercise that I want you to try. Right, I want you to try to do something related to JIT for quite some time, and I think doing a JIT specifically for Brainfuck is ideal because Brainfuck is such a simple language. Right, so you can Google up like Brainfuck. It's a language like with literally 8 commands, and it was designed specifically to make it easy to write compilers for. Not make it easy to program in, but easy to write compilers for. Right, so here are all of the commands, right? So essentially it's like a simple Turing machine, right? So you have a tape with the cells, and each cell has 255, range from 0 to 255, right? So it's a single byte. You have commands that move the head, right? So left and right, you can increment the cell by 1 or decrement cell by 1. They wrap around when they overflow and underflow. Then you can output the current byte to standard output, or maybe read from the input, and you have the loop commands, right? So for example, if you encounter open bracket, if the byte at the data pointer is 0, then instead of moving to the instruction pointer forward, you go to the corresponding closing thing, right? And if you encounter closing thing, if the byte data pointer is non-zero, instead of moving to instruction pointer, go backwards and stuff like that. So this is basic loops, and they also simultaneously conditions, right? So because as you can see, they're not unconditional jumps, they're conditional jumps. So you basically use them to implement both just loops and branches and stuff like that. So that's the entirety of the language. It's a very simple language, but very difficult to master, right? So, and right, I'm gonna give the link here, and for people who's watching on YouTube, it's gonna be in the description as usual. I think I forgot to prepare the description, so let me quickly do that. So this is gonna be references, and where is my title? I'm gonna quickly grab the title. So this is gonna be the thing. So what is a JIT compiler? Right, so essentially you can implement an interpreter for this language. It's actually quite easy. You grab the source code, right? So for example, we have some examples in here like hello world. You can grab the source code and you just iterate through each individual character and interpret it. Right, so, and that's gonna be fine, but like, I mean, it's just like very easy to implement. So you can try to implement the compiler, right? So this thing is very easy to translate to assembly, right? To assembly, and then assemble with assembly into an executable, and you're gonna have a native program. It's also very easy. So JIT compilation is a little bit more interesting, I think. So essentially it's gonna be mixed between interpreting and compiling. So the idea is going to be you take the source code and you compile it to machine code in the interpreter. So the interpreter compiles it into machine code in memory, and then instead of interpreting it, it basically jumps into that machine code and just like literally executes that code. And then returns and continues executing the interpreter. So this is basically how JIT compilers work, right? So they're like interpreters, but at the same time they're compilers, right? So while interpreting, they compile the program into the machine code in memory, and they execute that machine code, and that achieves the performance of native compilation, right? So It's a mix between native compilation and interpreting. So, and how we usually implement that, right? So usually operating systems, specifically Linux, have a syscall that allows you to map memory pages, and one of the things you can do with that specific call is that you can specify the protection, right? And protection allows you to set something like executable. So you can basically allocate some memory pages with executable rights. And this is where you may want to, put the machine code, right? So, and any machine code you put in that page is going to be executable, which means you will be able to call it like a function, right? So, which makes it pretty straightforward, like on the paper, to implement the JIT compiler for Brainf, but I never really tried that. So that's going to be the topic for today's stream. Just go ahead and try to implement a JIT compiler for a Brainf language. Right. So at the same time, I think it's also pretty good, maybe interview question for some hardcore software engineering and stuff like that, but maybe not. I don't know. All right, everyone progress in React today. So let's go ahead and create a folder where we're going to be doing all of that. So I'm going to call it BF JIT, I suppose, right? So the spelling of this name is actually kind of goofy, right? But that's fine, I suppose, right? So BF JIT.c. So that's going to be main executable. We're going to be implementing that in C because it is very easy to call mmap from C and do all of this like low-level unsafe operations and stuff like that. So we're going to be using C, of course, right? So let's go ahead and let's just create like a hello world, the usual hello world, the usual stuff, right? And we're probably going to be using knob for building as well, right? Because it's very useful. It also contains dynamic arrays, and dynamic arrays is something that I probably will need in that specific project, right? So dynamic arrays are always good. I would even say it's just like for a modern programming language, it is mandatory to have some sort of dynamic arrays, right? So it's just like a main data structure that we in modern software development use day to day, right? So we can't really live without that data structure, right? And it's such a shame that, C doesn't have them out of the box, so you literally have to implement them yourself, but it is what it is and it isn't what it isn't. Apparently, it is very easy to implement dynamic arrays yourself in C. If you don't believe me, check out the implementation in knob. That's basically the entirety of the implementation, right? So here it is, it's 11 lines of code. That's the entirety of the implementation of dynamic arrays, right? So anyway, so we need to enable go rebuild yourself technology for this script. Go rebuild yourself technology. That's quite important. You supply the arguments because it determines that it needs to rebuild itself from the arguments, right? So that's quite important. And in here we can just do something like, I don't know, knob log, knob info, and I'm gonna say simply hello world, right? So, and I'm gonna bootstrap the build system like so, knob.c. Hopefully it will simply work. There we go, the system has been bootstrapped. The first thing we wanna do, we wanna create knob.cmd, right? So here is a knob.cmd, and here we're gonna be appending some commands. So it is going to be cc, right? And we're gonna just build the bfjit, right? So bfjit from the source code. But I personally would like to also enable a bunch of commands in here. I think they're gonna be useful, like all of the warnings. So maybe even extra warnings, it's always useful. Maybe, I think it's going to be super important to enable the debug information because we're going to be looking into this kind of stuff in a debugger. Right, so we're definitely going to be stepping through the debugger, especially when we generate the machine code. And when we call that machine code as a function, I want to be able to step in the debugger and actually see the, the assembly that we generated. I think it's going to be very useful and very insightful. Right, so yeah, after that we want to do ncmd run synchronously, right? I want to run this entire thing synchronously, and if this thing actually fails, we're going to return non-zero exit code. So I'm going to just try to run this entire thing, and as you can see, we successfully created bfjit. There you go. So here is bfjit. So what I'm thinking is that maybe I'm going to start with implementing an interpreter first. Right, so then we may even try to compare their performance and see how they go. So, yesu. And definitely the first thing we're going to be doing, I think, before even trying to interpret the brainfuck or even try to compile it to machine code, we need to compile it to intermediate representation, right? So, because I don't really want to like work with characters directly, right? So we may try to just iterate characters, and if we encounter characters, we can try to interpret it as an action. But it would be nice to have some pre-processing step that at least figures out where this motherflippers has to jump, if you know what I'm talking about, right? It would be kind of nice to figure that out, right? Because if you just right away start iterating these commands and you encounter this thing, and for example you figured out that, you know, this current cell is 0 and you need to skip this entire thing, how do you skip that? You skip that in a very inefficient manner by just like maintaining the stack and finding the opposite one. It would be nice to sort of pre-compute all of the jump addresses for all of these brackets and stuff like that, and make sure, by the way, that the brackets are balanced before trying to interpret that. So that calls for a special compilation step from the source code to intermediate representation that checks if all of these things are balanced and figures out the sort of destinations jumps for all of the brackets and stuff like that. And we're going to be interpreting that intermediate representation rather than the source code directly. And that intermediate representation is something that we're going to actually compile to machine code. Right, so I think that's going to be the idea. You know what's interesting? On top of that, the intermediate representation may do a little bit of optimizations. For instance, it can collapse the streaks of pluses, right? So essentially intermediate representation, instead of like having a single plus, it may have like plus, you know, 8, right? So we have 8 pluses in here, right? So, and then maybe like -3 and stuff like that. So that could be a thing, actually. That could be a thing. And, right, so the intermediate representation for the brackets is going to be literally like a conditional jump with an address where to jump without regarding whether they are balanced or not, right? Without even regarding whether they're balanced or not. So the intermediate representation for the brainfuck could be a completely different thing. Right, then not really completely different thing, but rather different, right? So it's not necessarily one-to-one correspondence in here. This is something that we may want to do. Anyways, so let's actually go ahead and maybe introduce enumeration for OP kinds, right? So what kind of, you know, OPs we're gonna have? We're gonna have OP, you know, increment, right? So for the plus, OP decrement. So then OP left, OP right, right? So basically moving the head left and right. Then you can have input and output, right? And then you're gonna have two kinds of jumps, if I'm not mistaken. So you have sort of forward jump and backward jump. So if the byte at the data pointer is 0, then instead of moving to the next instruction forward, jump to the matching this thing. So if it's 0, skip an entire thing, right? And if the byte of the data pointer is non-zero, right, so basically return. So essentially jump if 0, right? So if 0, and jump if non-zero, right? So these are the sort of like OP things that we may want to have, right? And then we're going to have something like OP, right, and this is going to be OP kind, right? So here's the kind, and what's interesting is that since we're going to be collapsing some of the operations, right, instead of a single increment, maybe we're going to store the amount of increments that you want to do, right? So, and in that case, maybe we want to have some sort of an operand, so size t operand, right? And for increment is going to be how many times you want to increment. For decrement is going to be how many times you want to decrement. For left is how many steps you want to make to left or right. And inputs is basically how many characters you want to read, right? So which doesn't really make any sense, because usually you want to read one character into the cell, then move and stuff like that. But I mean, why not, right? So why not? And for output, the same thing. And for jumping, the same operand that is used for storing the amount of increments and decrements and left and right could be used to store the address where you want to jump if something is 0 or if something is non-zero, if that makes any sense. Right. So that's basically going to be an intermediate representation. I think it's kind of good intermediate representation because it's interpretable, right? So you can just go ahead and interpret it very easily. And it's also compilable, right? So you can generate machine code out of it. So yeah, I think that's pretty good. I really like that. And as the first pass, we don't really even have to collapse anything, right? For now, we can just like implement you know, inks uncollapsed and implement that later. So the intermediate representation sort of like, you know, has the room for that optimization in the future. And since we're going to be collecting the operations into sort of like an array, we need to have a dynamic array of operations, right? So let's actually have something like struct ops, and in here we're going to have some items, and of course this is going to be count, and of course this is going to be the capacity. There we go. It's going to be count, and this is going to be a capacity, and this is basically where we're going to store our operations, right? So let's actually see how we're going to do that. So I suppose we're going to be accepting the program. We're going to be accepting the program from the standard input, right? So this is a hello world, right? So this is a hello world. So let's actually put hello bf in here. Right, and essentially the way we're going to use that, we're going to supply that through command line arguments, and it's going to just, you know, execute that and print the output and stuff like that. So I think that's reasonable. So because of that, we're going to be accepting args. So this is going to be argv, and in here we're going to do a program. So nob shift args, and this is going to be probably argc. Can you see scheiße in this mist? And this is going to be argv. Right, and if argc is less or equal than 0, we have to say, bruh, you didn't provide scheiße. What is this? Half and scheiße? Provide something. Please provide something. What is this half and scheiße? Was ist das für ein half and scheiße, meine Freunde? So what we want to say, usage, right? So, and we're gonna have input bf. So the input is gonna be mandatory. Then we're gonna have, it's actually not info. I would like to say it's an error, right? And in here we're gonna say no input is provided, right? And then we're gonna just exit with non-zero exit code. All right, so after that, we need to read an entire flipping file, right? So this is writing an entire file, but we need to read entire file. There you go. There you go. So, and in here, we are going to have the string builder. String builder. We're going to put it in here. And here we have to provide the file path, and the file path is something from the input, so this is going to be something like this. So file path yusu nob, Jesus Christ, bruv. Emacs sometimes just like going fucking crazy. Right, so this is going to be argc, argv, and there we go, we have a file path. And then if this entire thing failed, we're going to return non-zero exit code, and there we go, we read an entire file. We read an entire file, and what we want to do with that file, we want to actually iterate it character by character. Right, so this is going to be sb count plus I, and in here, how we're going to handle that? We're going to take the character, and I suppose we're going to switch upon that character specifically, right? And if we encounter something like plus, we're going to do a very dumb thing. We're going to append to obs, da append. We're going to append the increment operation, believe it or not, right? So we're going to do something like OP, all right, like this. And we'll probably have to wrap it in parentheses like this, but not necessarily. We can actually extract it into a separate sort of like operation, so it looks a little bit nicer. Maybe even like this. And in here, we're going to supply the kind, and the kind is going to be OP kind. And the actually not OP kind, but OP increment, not input. Increment is operand, and this is going to be 1. So as I already said, we don't really handle the streaks right now. We don't really collapse the streaks. Right, we're going to do that a little bit later, and we just like append this thing. Right, and then correspondingly for the minus, we're going to do decrement. And so on and so forth. And most interesting thing is that what we're going to do if we encounter something that, like unrecognizable character. If I understand correctly, usually brainfuck interpreters literally ignore that. So as you can see, everything that is not one of these commands is literally a comment. So the interpreter is going to just ignore that. Which is good, which is something that we probably want to do as well, right? So essentially, if you encounter something that is not one of the commands of brainfuck, we're gonna ignore that. Easy peasy, lemon squeezy. Am I right? Meine Freunde, am I right? I do think so. But how will we even handle the like streaks? If you want to handle the streaks, how are you gonna do that? So you encounter the plus, right? And then you may try to do something like while let's say I is less than SB count. Maybe we want to even do something like 4, right? And then we're gonna do plus plus. And another thing is that SB items I is still equal to plus. Right, so we're gonna be just like keep incrementing and keep counting how many of these things you like have. Right, so plus plus 1, and then you just like use count. But at the same time, if you encounter something that is not a correct command, you still wanna include that into a streak. You know what I mean? Right, so essentially, if you, like, this is going to be a single streak that you want to collapse into a single increment, like plus 8. But what if you put space in there? Will that split that into streaks instead, right? So you kind of need to handle that. Which probably means that maybe you need some sort of a tokenization step, right? That basically gives you the next valid command or something. So we need a simple lex. Yeah, so we kind of want to have like a simple Lexa and stuff like that that handles all that. That's actually kind of funny, and the Lexa is going to be actually super simple if you, right? It's not going to be like anything super fancy, all right? It's nothing super fancy. It's just the, you know, maybe the string view, string view content and the position, right? And essentially in the Lexa you would do Lexa next, right? And it just gives you the next character. So this is going to be something like this, right? It just gives you the next character and whatnot, right? Which is all right, I suppose. And on end it will return 0. But essentially the point of that Lexa is to skip all of the non-command characters, if you know what I'm talking about, right? So just skip all of the non-command characters. So yeah. So maybe we can even do something like this. Assert to do not implemented, right? And here we're going to just return 0, and this one's going to be void L. And after we read this entire thing, we can just create a Lexa, right? So a Lexa is going to be content, which has the data, and the data is SB items, right? So this is SB items, and the count is the count, and the position is, of course, is going to be 0. So that should be enough for the Lexa. And right. So essentially, you probably want to do Lexa next, right? So we're gonna pass it by a pointer, and you get sort of the next command. But because of that, right, you have to sort of do the following thing: while C is greater than 0, or maybe just while C, right? Because in case of the end of the stream of the tokens, we're going to return like 0. And if we encounter plus in here, right, if we encounter plus, we may want to continue like doing this thing. We may want to continue doing this thing. So the count is obviously going to be, you know, 1. It is obviously going to be 1, and while c is equal to plus, right, we keep incrementing, right, while it's equal to plus, we keep incrementing. And then, yeah, that is it. That is the entirety of the thing I wanted to do, actually, believe it or not, right? Because essentially, if you encounter end of the stream, right, it's not really actually, right, so you need an additional this thing. If you encounter the end of the stream, the loop is gonna end, you're gonna add the last thing in here, and then on the next iteration, you're gonna check C, and C is equal to 0, so you're gonna just quit. You're gonna just like straight up quit, which is okay, I think. And you can repeat this sort of like a streak thingy for literally all of them. Interestingly, for literally all of them. So for literally all of them. And what's funny is that you wanna do that streak compression for all of the things, like case this, case that, right, case that. Like you want to do that for all of them, except inputs and outputs. So that means you probably want to kind of abstract it away, if that makes any sense. So here we're going to have C1, and while C1 is equal to that C, original C, all right, you keep incrementing it, and because of that you can use it like this, and you sort of like a compressed the compilation of all of these separations, and you never have to even think about this kind of stuff anymore. So furthermore, you probably want to do the following thing. Yo, that is actually kind of cool. All right, this is actually kind of cool. So what's the input? So I don't quite remember. Like, why am I having so much fucking fun doing that? So output. So this is the right. So this is the output. Dot is the output, and input is this thing. Right. So this is that, and this is that. So we can kind of like want to use the same values as the characters and stuff like that. I think we can even align this entire thing so it looks freaking cool, doesn't it? I think it looks freaking cool. Right, and right, because we sort of like abstracted all of that away, right, we implemented that for all of them, I think. So, which is kind of cool. But I don't know what would be cooler, like keep it like that, or maybe keep it like a single thing. I don't know, maybe I'm gonna just do it like this. Right. So for all of them, you're gonna implement this sort of compression. Right, so we're gonna implement this sort of compression. I'm still not sure, is this better? Or maybe this better? I think this one is better. So anyway, so for this thing, I would like to come up with a completely different name. I think C1 kind of sucks. Right, so since we're computing this streak, so let's actually call it S. Right, so let's actually call it S. So we're sort of computing this streak. And that is basically, so the only thing we'll need to handle in here is these two things, right? So we'll need to handle these two things. And I wonder how well is it going to work. So for now, I'm gonna say something like to do this thing is not implemented, and for the other thing, that thing is not implemented either, right? So something like this. So let's try to compile this entire thing, because I've been slapping the code for quite some time. I'm not sure if this mother flipper even compiles, so it probably doesn't, right? So let's go to the compilation errors as usual. We don't even have knob string view in here, so it's not even a thing, because we don't even include knob in here. So we should be including knob. So I'm going to define knob implementation. What else do we have in here? So I forgot the semicolon, no big deal. I don't use program. I should be using program. I'm going to put it in here. Boom, everything compiles, easy peasy, lemon squeezy. All right, so I would like to maybe even print maybe even print the you know, ops that we collected in here. So I'm gonna go through all of the operations that we collected. So it's gonna be ops count plus plus I, and so what we're gonna do? So I'm gonna just print you know, the character, maybe just the character, and the amount of operands that we got from there. So it's gonna be ops items. This is gonna be the kind, right? So the kind that we got, and ops items I. What is it called? Operand, right? So this is the operand, and we're gonna just print them like this, and we're gonna see how it goes. So this is gonna be bf JIT. We're gonna provide hello, and it's not gonna even compile because right, so there's no lexer next. Okay, so how are we gonna approach this entire stuff? Right, so if the position is greater or equal to the content count, that means we exhausted the entire lexer. We're gonna just return 0, right? We exhausted the entire lexer. And another interesting thing is that maybe the first thing we want to do, we want to strip away everything that is not a legit command, right? So maybe we need to have some sort of a function which is called isBF CMD, which just accepts a character and answers like a very simple question: is that a legit, you know, brain fuck command? So as far as I know, there's functions like str, or maybe strchr. I think that's the one which locates a character within a string, and this is something that we could use. We can actually list all of the valid brain fuck commands in here, like so. And we can even maybe put something like char cmds, right, and then do strchr, cmds ch, and then if it's not equal to null, that means it is in fact a valid bf command. I taught you well. I'm really proud of you, chat. Yes, I'm really proud of you. Anyways, so nobody throws any money anymore. Anyway, while so we're gonna have this thing, right? While this thing is less than content and is bf cmd el contento el position, if while this thing is not a valid command, what we're going to be doing, we're going to be just incrementing el position. All right. As soon as it becomes a valid command or we reach the end, we're going to do something, right? So if this thing is greater than, you know, the count and stuff like that, we reach the end, there is nothing to return. Otherwise, what we have to do, we have to maybe, you know, in C, there is a very cool way to do all of that. You can literally just return, yeah, freaking C. Right, so essentially, since it's a post increment, the entire expression is going to return the old value, right, but it's going to modify position. So that way you can return this entire thing like that. And furthermore, because of that, you can actually compress this entire thing like this. So look at that. Look at that shit. It's horrible. It's horrible. So what's funny that a lot of like modern languages that is supposed to like compete with C and C++, they don't have post and pre increments, right? Because this shit is kind of crazy, honestly. But I guess that's fine in here, right? So let's do recompilation. Let's do recompilation and see how it's gonna go. So the content, it's actually called not items, it's called data. I did a fucky wacky and oopsie doopsie chat. So please forgive me my fucky wackiness. And funny, nothing is happening. Nothing is literally happening because I have no idea why, honestly. So what the fuck is going on? Right. So because, yeah. I see. I see. So essentially, we never actually take the next C. Right. We never actually take the next C. So what we want to probably do, right? We want to then, after we're sort of like done, assign the last thing that we got from that string. That's what we want to do, right? So we're going to kind of assign the last thing that we got from that string, and that is it. So we actually reach this entire thing, so this stuff is not implemented. But to be fair, who fucking cares? Let's just ignore them, right? So essentially, when we encounter those motherflippers, we're going to just take the next character. We're going to skip them for now, right? We're going to just skip them for now and implement them later, because I just want to see what we've gotten here. So as you can see, we have 8 pluses. Is that true, chat? Is that true? So let me see. So do we have 8 pluses? We do in fact have 8 pluses. Look at that. That is very poggers. Then we have a 1 to the left, 4 pluses, and as you can see, we have an intermediate representation that actually collapsed all of these things. It in fact collapsed all of these things. So that is pretty cool. Right, and so what's funny is that we implemented the collapsing of the strings once, and we reuse it for all of the 6 separations in here. Right, so we reuse it for all of the, 6 separations. So, okay, next thing we need to do, we need to, figure out the, the jumps and stuff like that. We need to figure out the jumps and stuff like that. So we don't really need to do these tricks for the brackets, right? Because this is not how they work. They're kind of like a special commands in that regard. All right, and essentially, I suppose one of the things we can do. So operand, we're going to set the operand to 0, and operand for that specific kind, which is jump if 0, is going to be the address where we're jumping. But we don't know that address yet. So what we need to do, we need to maintain the stack of the addresses of these brackets. The stack of the addresses of the brackets, so we know where to go back and back patch it. Do you guys know there's a back patching in language development? Right. So essentially, you quite often, when you develop in a language and you're generating like a target platform code or something like that, you have some operations that either read or write into the memory or jump to specific things, but you don't know where that memory yet, or where is that specific thing yet. So you just place the thing, the read or write or jump, and continue generating, but you remember where you placed it. And once you generated everything and you figured out all of the addresses properly, you go back to your list of things you need to backpatch, and you backpatch it like this. So that's backpatching. Right, so I think it's like a legit term, backpatching. So if you essentially Google it up, you will find like articles, backpatching and compiler design and stuff like that. So that's basically what it is. Two-step compilation, you can call it like that. All right, but I think backpatching is actually a really good name because it's self-explanatory. You can literally kind of see from the name what it does, right? So you go back to what you generated or what you compiled and kind of fix, you patch it, backpatch it. Right, I really like this name actually. So it's on Geeks for Geeks, so it must be true. Freaking Geeks for Geeks, I swear to God. I wonder if the website like that completely switched to a ChatGPT generated content. I wonder. I wonder if they did. Anyways, let's continue. So we need to maintain the stack, right? So let's actually maybe introduce something like struct, and we're gonna call it addr stack, right? Addr stack, and we're gonna just store like sizes in there, right? So this is gonna be the items, and in here we're gonna have a count, and here we're gonna have capacity. Right, and so we're gonna just allocate addr stack. So this is the stack, boom, there we go. So, and the address that we want to have in here, the address is going to be the current size of the ops, right? So essentially, you have a bunch of elements in the list, right? So essentially, you have 5 of them. They're indexed from 0, 1, 2, 3, 4. So the next element that you're going to put in here is going to be at the index 5. So that means the address of the element that you're about to insert into the list is the current size of the list, because you didn't actually put anything in there, right? So that's why I'm sort of remembering that before I append that thing into the list, right? So this is going to be da append. So this is ops, and I put open there, and address actually stores the address of that specific thing in there. And in here, you want to actually do append to the stack, and we're appending that specific address in there, right? And then we look for the next thing in there, right? Look for the next thing in there. Epiku. So yeah, and essentially, when you encounter the closing thing, you need to pop an address from the stack. First of all, you need to check if the stack even has anything in it, right? So if the count is equal to 0, that is straight up an error, right? You encountered unbalanced brackets and need to report that. You really need to report that. So when you're reporting that, it would be kind of nice to also specify the place where that Haufen Scheiße has happened. Stack underflow, yeah, so stack underflow. But we don't keep track of those things, unfortunately. We don't keep track of those things. So one of the things, well, we do kind of keep track of that. New word. Yes. I already told that story. One day, I opened a Twitter, like while having German IP, right? So because Twitter is banned in my country, and I looked at the trending panel, and in the trending panel there was a phrase, Haufen Scheiße. How to spell Scheiße? I don't know how to spell Scheiße. Right. So, and that word burned into my retina. So now, right. Oh, it's like this. Yeah, there we go. So, thank you so much. Right. Scheiße, Haufen Scheiße. So it was trending in Germany on Twitter. So now, and my sick, ill brain just remembers that. So I can't forget now. That's how I learned German, by the way. I'm really sorry, German people. It's a perfect summary of German politics. Yeah, it's actually a good summary of any politics, I suppose. It's kind of funny, you don't know how to spell Scheiße considering how often you say it. Because I'm learning languages like a kid. Right, because kids first learn how to speak that language, not how to spell things in that language, right? So, yeah. What's funny is that quite often, even though English is my second language, I quite often struggle with spelling too, right? Because I talk a lot in that language, and sometimes like I don't know how to spell a specific word that I use, right? It's kind of funny actually. So how to swear in that language is actually very important knowledge here. In fairness, though, English spelling, yeah, exactly. English spelling is just like, it's like you literally have to memorize it. It doesn't really have rules. It has patterns, right? So English spelling does in fact has quite a few patterns that you can memorize that can help you, but there is no really well-established like formalized rules, if you know what I mean. All right. So here's the interesting thing. So there is a list of so-called irregular verbs in English. And when you learn in English, you're told that they don't have rules on how they're spelled and how their ending changes and how their form changes. You literally have to memorize them. So there's no rules for irregular verbs, and that's why they are irregular. But this is a lie, isn't it? If you studied English and you studied irregular verbs, you know that there are some patterns in there. There are some patterns, right? So because the words like understand and stand, they actually have a similar forms, right? So there is no rules, but there are patterns. And English, yeah, fought and thought, yeah, exactly, fight and stuff like that, right? There is no rules, but there are patterns. So, and English is like that throughout the language. There's a lot of moments in English that there's no really rules for things. You literally have to memorize, but there are patterns. Right. And that's what's interesting about English. That's what's interesting about it. And maybe those patterns, those sort of like irregular patterns come from the fact that English was influenced by so many different languages, right? So because English is in fact influenced by a lot of languages, So anyway, so we don't really know the position where all of that happens, but that is not really true, because in Alexa we have pause, don't we? I think we do. So, and that's something that we can actually use in here. So essentially I can say, okay, so here is the file. So, and then I'm going to put the position in somewhere in here. So this is going to be file path, and this is going to be position. And right, so we're going to say unbalanced loop or something like that. So we have unbalanced loop. Maybe even something like this, and we're going to just return 1. And in here, maybe I'm going to just even say error. So I'm not going to be reporting line or column or anything like that. I'm going to be reporting the character, right? So because I don't really want to spend too much time thinking about all that, right? So it's easy to report like a byte offset. Wait, didn't Casey recently like made a whole, like a huge article about how it is much better to report errors for the compilers by just providing the byte offset rather than lines and columns? I think Casey, like a huge article, I didn't even read it because I agree with him. Right, I know as a person who developed compilers and interpreters, I know exactly what the fuck he's talking about. And not only that, I also developed text editors, so it is also a thing in the text editors. Like, I know precisely what he's talking about, so I didn't even read like a wall of text, because I kind of knew what he's gonna talk about and like all of the arguments and stuff like that. Because if you try to develop a text editor or a compiler or both, you know how it goes, right? You don't really need to like know all of the wall of text of that. So it's kind of funny actually. Can you share that article? It's a computer enhance. So let me actually see. But again, I didn't read it. Case Moratory. Yusu. No thanks. Okay. Byte position are better than the line numbers. Yeah, there we go. So it's this one. So he's talking about algorithm, right? Yeah, I saw. Yeah, so O of 1, O of n different. Like I literally know what he's about to say. Like I know because I saw all of that when I was trying to implement all of these things. Yeah. So, and by the way, I think I need to put that in the description as well, because I'm pretty sure I'm gonna not cut out that bit from the final vote, right? So it's probably gonna be in the vote as well. So I'm gonna put that in the description for YouTube people as well. Yes, YouTube people, you don't see everything we do in here on Twitch, unfortunately. So follow me on twitch.tv/Twitter for all of the dirty secrets that I don't put on YouTube. All right. So anyway, so we have the thing in here. So we need to get a thing on the top. So this is going to be count -1. Interestingly, one of the things we can do. Yeah. Freaking Why is it so convenient? All right. Sometimes using like post increment and decrement is so convenient in some particular place. I feel bad about using it. It's just like it's offensively convenient to use it in here. Just like, what the fuck. Anyways, so yeah, let me see. If the byte, instead of moving to the instruction, jump it forward to the command after the matching. Okay, so you literally need to skip that thing. You literally need to skip that. And I wonder how we're going to be doing all of that. So essentially that means we need to create an OP and only then back patch stuff, right? So that's what we need to do. We first need to create an OP. And if the data pointer, instead of moving to the instruction pointer forward to the next, jump it back to the command after matching plus. All right, so that means that that OP has to be actually kind of like the address of that thing, but after, like so. All right, it has to be after. All right, and then essentially we need to do nob da append ops, then we do OP, and then we go into ops items address, and we set operand to ops count because it's going to be the value after the corresponding matching thingy. Boom, we implemented the sort of like the loops, right? We implemented la loops. I think so. And so let's actually try to run this entire thing. It's not easy to see if we did that correctly, right? So yeah, so it has to be like 30 and stuff like that. So maybe we also have to provide the address. So let's actually also print the address of this thing. All right. So essentially, so you have to jump to 30. So that means there is a 30 and it's after, yeah, it is actually after the corresponding thing. And this one jumps to 2, which is after the corresponding. Okay, so we figured out the addresses of all of them correctly. Right, so there we go. So we compiled Brainfuck to an intermediate representation. We compiled it into an intermediate representation, and the only thing we need to do now is to interpret it. Right, so we need to interpret it. Right, so how are we going to do that? I suppose one of the things we want to do, I want to allocate some memory, right? So let's maybe introduce type def struct memory. So it's going to be basically array of bytes. So I want it to be like sort of stretchy, right? So it's going to be allocating as we go. Capacity, so you're going to have a memory, right? So you're going to have memory. And so then mu it's from the description, I see. So sometimes autocomplete just autocompletes random stuff from different files. We want to have a head, right? So the head is located somewhere here, right? So that's what we're doing here. And we also need to have the pointer to the current command, right? So this is basically what we're going to have. So it's IP0. So let's go ahead and just do while IP is less than ops count. We're going to keep doing all of that stuff. So I'm going to switch case on ops items IP kind, right? So it's going to be like that. And if I encounter something like, what is it called? OP increment, right? If I encounter OP increment, it is actually super straightforward. So what I want to do actually, I want to do nob di append memory 0. So essentially, every time I do increment or decrement, I want to make sure that if I access a cell at the current head, it is available, right? And I'm going to do plus plus ops. Actually, what is it? Ops items IP operand. Is it going to overflow correctly? That's a good question. Maybe it will, maybe it will not, I don't know. But anyways, so I'm gonna just do +1, and there you go. So then we need to do a decrement, like this. And then we are going to do left, right? So we're gonna do left, we're moving to the left. And essentially, this one is really interesting because, all right, we may want to report runtime errors if IP is less than ops operand. All right, we want to report an error, right? Because we don't really go to the left indefinitely. We're going to be going to the right indefinitely, but not to the left. So in this specific case, we want to report something. Right, so this is going to be sort of like an error, maybe a runtime error. Memory underflow. Right, so yeah, I think it's a memory underflow. You're trying to access the memory that is like too low, and we're gonna just like exit with that. But if they're equal or something else, we're gonna just like it's not really IP per se, actually, it's a head, right? It's more of a head, and if it's something like that, we're gonna just do this kind of thing. Would it be better to maybe factor out ops items IP to just op? Like this, so we can just query replace this thing with op. I think that's much better. I think that is in fact much better. Yeah. Op right. And what's interesting is that, okay, so head plus equals op operand. So that is understandable, but if head is greater actually or equal to the memory count, right, to the memory count, we have to keep incrementing it, we have to resize it. I think the easiest way would be to just do something like this, right? To just do something like this. Right, so keep incrementing it by 1. Since the append doesn't really do memory reallocation on each append, it doesn't really matter, so I think that's totally fine. It's kind of dumb, but I mean, it is what it is. So anyway, so increment, decrement, left, right, and stuff like that. So this is going to break. Then OP input, right? So I don't think we use input here anyway, right? So maybe for now, I'm going to say that it's not implemented. Right, so I don't think it's important right now to do input is not implemented. Right, so input is not implemented. Output is more interesting in my opinion. Output is more interesting. By the way, I forgot to all of these cases, in all of these cases, to increment IP. I think that's kind of important. Also in here, increment IP. But what we're going to be doing here, we're going to just print the character. We're going to just print the character like so. Right, and what's the character we're printing? We're printing memory items head. That's the character we're printing. So input, output, and that's it. So the last thing we need to have in here is a jump if 0 and jump if not 0, right? So case. So that should be straightforward. So if memory items head equal 0, we just do IP equal OP operand, we just jump there. Right, so having this intermediate representation actually makes interpretation so much easier, and compilation as well, right? When we go to the compilation, you will see how easier it is to do the compilation once you have this intermediate representation, which already handled all these corner cases and stuff like that. Right, so it sort of handled all of that for you, so you don't have to worry about it when you're you know, interpreting this entire thing. So let's go ahead and try to compile, and that compiles first try. So we can try to interpret the hello world and see if it's going to print that. Hello world. which is kind of weird. Like, is that a fucky wacky on my part? Like, where is the second owl? So, it's kind of hard to tell. So here's the hello world. We can try to maybe copy that thing in here, or I could be actually modified something. All right. So this is this program prints. So do they use? Huh. Okay, I suppose we don't have to do that. I'm not sure how it's going to work with all of that stuff. But anyway. Yeah, is that a bug in my thing or what? I think it's the double dot that is not executed. Oh shit, you're right. You're right. So thank you so much. Double dots. We have to handle that. Okay. So goal of coded. Huh. So maybe I should not do the tricks for the input, but maybe that's fine. All right. So output while maybe op rand plus I. And okay, there we go. Thank you so much. Yeah. So hello world, first try by the way. Dub. So yeah, and we have a thing that is interpretable, right? But the next thing we need to do now, we need to take that intermediate representation and we need to compile it to assembly. And execute it, and all of that at runtime. And yeah, I already streamed for 1 hour, and I would like to make a small break because I need to refill my cup of tea. So I think we're gonna do that on the second part of the stream. I'm actually quite productive. Like, I implemented like a pretty cool brainfuck interpreter in 1 hour, unprepared or anything like that, right? That's actually kind of cool, and I really enjoy that. Like, I kind of like the fact that I discovered this sort of like a strict compression idea. Right, this is actually so cool. So it's kind of funny that you can just do that. Right, so really like that. So yeah, let's make some break. And all right, so what we need to do before we can even compile this entire shite to a machine code, we need to figure out like the mechanism through which we're going to be even executing that machine code. So what I want to try to do, I want to try to come up with a sequence of bytes, right, that I will try to jump to in a C program, right? And what's going to be the sequence of bytes? We can just basically write a simple hello world, I suppose, right? So just like write a simple hello world, put it into like a sequence of bytes as a payload, right? And just try and jump there. Just try and jump in there. I think that's going to be kind of fun. So, but before we can do that, I think I need to first write that in a proper assembly, right? And compile it to ELF and just make sure that I have like a sequence of instructions that actually works and produces the hello world. And then we can see how we can figure out the machine code out of that. So let's write a simple hello world in assembly, in x86-64 assembly. So it's going to be hello asm. So it uses FASM, NASM. I want to use FASM actually. I don't have a FASM mode in here. What the fuck? Do you have a FASM mode for Emacs somewhere here? Because I do remember that I had something in here. I do have a FASM mode. Alright, so that means that maybe I just don't include it anywhere in here. So maybe what I have to do is just like require local. Yeah, so this is where we add to the path. So I probably want to do FASM mode in here. There we go. So that means later in here I can switch to the FASM mode. Okay. So my favorite assembly is actually FASM or flat assembly. I really recommend to check it out. I like it much better than any other assemblies like NASM or whatever, because it's extremely minimalistic. It's so minimalistic, it's actually written in itself. Like, it's completely written in itself, and it is capable of producing like a static executables and stuff like that. It's actually quite amazing. It is actually quite amazing. So I really like shield that specific assembly over any other assembly because I like it so much. Right, so NASM is written in C++, if I'm not mistaken, or in C or something like that, right? So it needs a high-level language. FASM is written in itself. And on top of being written in itself, it has like a really powerful meta-programming language, like a macro system and stuff like that. It's fucking insane. So anyway, so I want to actually go to the description and shield my favorite FASM a little bit. I really like it. So anyway, I think you're supposed to do like a format ELF64 executable 3. Right, I don't quite remember. Like, I think you put 3 in here or something. We can even try to just do FASM hello and see if it's going to... yeah, it already compiled. It compiled it into hello with 64 bytes, which is the size of L64 header, if I'm not mistaken. Yeah, it literally... it literally just generated the L64 header. Right, which doesn't really do anything, so that's actually kind of cool. Right, so that's actually kind of cool. So it's gonna be hello, and so exact format error. So that is totally normal. That is totally normal. So then I think you specify the segments, right? So we can specify the segments something like text, and we can say that this thing is executable or something. Right, and we can say that entry is going to be main, and in main we'll have to do the rest of the stuff, right? So for now I can just like simply return and do nothing, and let's see if it's going to compile. So segment executable, I think maybe it's just, yeah, all right. So I think, oh, it's, you have to do sections. If you want to give them names, right? Segments in ELF don't have names, it's only the section. But hey, guys, do you know the difference between segment and sections in ELF? I've recently been studying ELF format, and it's fucking insanity, like holy shit. So essentially, ELF has a notion of segments and sections, and they're roughly the same thing, but not really. So segments are used by the loaders of, you know, dynamic libraries and stuff like that, and the kernel. Right. So essentially, when the kernel is about to load your ELF file, it looks at the segments and places them in memory and then jumps to the entry point and stuff like that. So segments are for the runtime and stuff like that. Sections are for the linkers. Right, so linkers shuffle around those sections. Sections can assign names and stuff like that, and symbols and everything. And at the end of shuffling around those sections, they will produce segments. Right. So that's the difference. And it is reflected in FASM, right? So you can actually create both sections and segments, right? So you probably want to produce sections if you want to link with something, right? If you want to link with something. In our case, we don't really want to link with anything, so we're going to produce like a segment instead, right? So segment. So, and we can assign different rights to that segment. We want this segment to be executable. Right, so there we go, and that seems to be compiling, right? And you've got an executable of 121 bytes. That's why I think, by the way, FASM is awesome, right? Because it allows you to create this kind of executables. So that's the entirety. What's the 3 for? I have no idea, honestly. I think it's not even right. Maybe it's a version of the format, but I remember that you have to do that. Maybe you don't even have to do that, so we can try to do. Yeah. So what if I just don't do 3? Yeah, you don't really have to do 3. So I don't remember what it means. So maybe you don't even need that shit. So fuck that. So if you try to run this entire thing, it's gonna segfault. Obviously, it is going to segfault. We can even take a look at the read elf and see. So where is the entry? Yeah, so entry is somewhere around here, which is rather interesting. So it's not exactly at 40000, right? So it's at 76, which is 120. So it is, oh yeah, so it places like the entirety of the file in the memory, including elf and stuff like that. So it figured out a really like weird entry point for the elf, but it doesn't really matter. Anyways, so the reason why it's segfault is because it starts executing, it tries to return, but there's nothing on the stack, so it basically returns to nothing or some weird place. And what we have to do instead, we have to call the exit syscall, right? So that's what we have to do. So Chromium syscalls, right? So there's a Chromium OS table of syscalls. I use it all the time, and this is because Chromium OS is Linux, so the syscalls are basically the same in there, right? So I really like this table because all of the search engines usually give me this table, right? So that's the only reason why I use it, because it's just convenient. So where is the exit code? Where is the exit? So it's 16. So as far as I know, in here we can actually do something like sysexit equals 60. Right, so essentially this is a part of macro language of FASM, right? So you can assign a macro, and there you go, you have a macro in here. So the syscall codes are located in racks, so we have to move racks in here. So this is going to be racks, and we're going to do sysexit. And the first argument is going to be in RDA, so RDA is going to be 69, so, and we're going to do syscall, there we go. So we called to the syscall exit, and we're going to try to run this entire thing, compile, and it exited abnormally, but look the code that it exited with. It exited with 69, so that means it worked correctly. So we have to put 0 in here, and that will exit correctly as well. So there we go. We learned how to call the exit syscall. Isn't that Polish? I think that's pretty freaking Polish. Yes, it is. So the next thing we need to do, we need to actually do move racks syswrite, right? So we're gonna have this kind of thing. So and syswrite is what? What is it equal to? It's equal to 1. So if I'm not mistaken, the first argument is fd, the file descriptor, RDI, we're going to put 1 in there, which is the standard output. So the second argument is RSI, pointer to the buffer. So we need to have something like message. So let's say hello world, right? And we're going to also put a new line in here. And we also need to have maybe message len. Right, so which is going to be equal to this minus message, which basically effectively computes the size of this entire thing. I don't remember if you have to put this thing in here, but we'll see. Maybe you do have to do that. All right, so we put the buffer in here, and then the size of the buffer is in RDX, which is going to be message len, and we just call to the syscall. There we go. So this is 2 function calls effectively in assembly. Right, assembly is not that difficult of a language actually. Right, so this is a single function call to the kernel and stuff like that. And message len was not undefined symbol message len. Do you just do equals? Yeah, you just do equals, and look at that. So it's a hello world. It's a hello world. So, and the size of the entire executable is 179 bytes. It's actually less than the source code itself. And we can open it up, and that's basically, so it's kind of funny how the binary code kind of corresponds one-to-one to the assembly that we actually wrote in here, because hello world is at the end. Right, it is at the end. What's funny is that I can put hello world before the entry point, and I think that is going to be kind of reflected in the final executable. We can give it a try, right? So, and I'm gonna open, yeah, so hello world now is right before the executable code. It's not at the end. So here comes the code itself. You see how it is in here, right? So then we can just go ahead and move it in here, recompile it one more time, open it one more time, and hello world is at the end. So there is like a one-to-one correspondence to what you write in this specific assembler and the final generated, generated code, which is kind of funny. But it's not really useful for us. It's not particularly useful for us because if we just take this entire file, load it into the memory, and jump to it, nothing is gonna happen, right? So it's basically will start executing starting from here. What we need to figure out is where is the entry point? Where is the entry point? But instead of figuring out that, we can just ask Phasm to generate like a raw executable. We can actually strip off all of that stuff. So we can say, okay, format is going to be raw. There is no segments since it's a raw format. And that's basically it. So that will generate you an executable. It's not going to be even executable. It's going to generate you a binary. Right. So it even complains about some stuff in here. So just a second. Let me see what's going on in here. So move racks 1. Illegal instruction. So I think it's something like bits 64 or something. Bit 64. Is it? I'm gonna brute force this shit. Does anybody remember? Phasm bit 64 format. So this one is, does it have to be first line? Maybe it has to be first line, maybe. Let me see. Bits 64. Damn, I don't remember. 36-bit mode. Phasm 64-bit. There was sort of like a macro or something like that. Does anybody remember Phasm as... Damn. And it's usually really difficult for me to Google on the stream for some reason. 64-bit raw format. Raw P format again, raw, maybe binary on x86. Okay, use, okay, it's not bits, it's use. Of course, you dummy dum-dum. It's use 64. Of course, if you want to do ELF, it's a format, ELF 64 executable. But if you want a raw format, it's use, obviously, you dummy dum-dum. It's so fucking intuitive. Anyways, I'm sorry. It's just like, I need to calm down. Right. So, and essentially, that's it. So this is the, the machine code of this entire program that you can jump into and start executing and stuff like that. Right. Which is kind of cool, I think. Which is kind of cool. But since we're going to be executing that shite in, in the memory, we don't really need to do an exit code. Right. We don't really need to do an exit code. We just need to do like write, and that is it. What's interesting is that if we're going to be jumping right into here from C, we're going to be jumping through calling a function. Right, we're going to be jumping through calling a function. So that means we need to return from that function afterwards. Right, so that's the thing we're going to have in here. Right, so that's going to be the thing. So, and let me try to do that. So hello bin. And that is basically the code that we can try to execute already. That's basically the code that we can try to execute already. And I wonder if, like, what kind of move it uses in here. Does it use the move that is, like, sort of relative or something like that? That would have been interesting. In any case, let's actually try to execute that shit. So I'm going to maybe go to... how do I want to do that in here, or do I want to do that in a separate file? So maybe I'm going to actually create runbin .c, which is going to be a completely separate thing. All right, so we're going to include knob.h, and we're going to define knob implementation, right? So, and then we're gonna just do something like this: argc char argv. Right. So and bf JIT.c. So let me just grab all of that stuff in here. Right. So and the input is going to be literally the binary, right? And essentially, that's the binary that you want to use in here, right? So we can even do something like noblog, nobinfo. S is ZU bytes, right? So this is going to be file path and SB count, and we're going to just return 0 in here. All right, so in knob, we're gonna simply build the second thing here. So it's gonna be runbin, and let me just try to do knob, not no, but knob. Okay, so what does it? Why doesn't it build properly? So what was it saying? Multiple knob file if not exists. Really? Why? Am I going crazy? Ah, I am going crazy. So I forgot to clean up the count, of course. Yeah. So that's a complete goof on my side, right? So you first need to clean it up, and then yeah, there we go. So that makes sense. That was weird. It was the weirdest shit I've ever seen. What the fuck? Anyway, so everything's fine. All right. So we're gonna do run, right, and it expects the thing, and it can provide the binary, not BF, bin. Oh my god. Okay, so 44 bytes. Okay, so it is loaded in the memory, and I wonder if we can just go right away and just try to call that thing. Okay, can we just try to call that thing? All right, so something like SB items, and I would like to call it like cast it to run or something like that. And run could be a function, right? So run is a function pointer that doesn't really return anything. It could return something potentially, but it won't return anything. It doesn't accept anything. Right, so that's the run functions. Then we do run. We just cast this entire thing to that, maybe even like that, and then call this function. And that is really interesting. Is it going to produce something? So let me do knob, and let's just try to run that. And we got a segmentation fault. We couldn't call to that function. And a segmentation fault usually happens when you're trying to touch the memory in the places where you're not supposed to touch it. And the reason is probably that specific memory is not executable. It is not executable. So you can't execute Scheiße there. So we touched the memory inappropriately. How can we make the memory executable? We can actually map a chunk of memory that is in fact executable and copy that thing there, right? So we can try to do that. People are being funny about all of that, yeah. So we need a function mmap, right? Depending on the operating system, it's going to be different, right? So different APIs provide different sort of things. So an address, what is in fact an address? So creates address. If address is null, the kernel chooses the address at which to create the mapping, right? So that means we can just put a null in there. So, and it doesn't really matter. So what's going to be the length? So length. The length argument specifies the length of the mapping, right? So the content of the file mapping are initialized using length bytes. So I suppose we can say that we need to allocate SB count amount of bytes, right? Because we're going to be moving that data into that specific mapping. So protection is the protection that we want to have. Argument describes the desired memory protection of mapping. Must be conflict. It is either none or bitwise or of several things. You know what I want to have? I want to have all of them, right? So let's just have all of them, all of the protections, if you know what I'm talking about, right? So just like, let's have all of those mother flippers. Give me all of the protections, and okay, so the next fun thing is the flags, and I don't remember how to use them. So map shared. So share this mapping. Updates to the mapping are visible to the other processes. We don't need that. We don't have multiple processes. Map shared. The flag provides the same behavior as map shared. We don't care about that. Private. Create private copy on writing. Updates to the mapping are not visible to other processing mapping the same file and are not carried through underlying file. That's probably what we want. We probably want to have a private mapping, right? So it's not carried through file or anything like that. We don't give a shice about file. So map 32-bit. Put this mapping first to 2 GB of the process. We don't really care about that. Anon, synonyms for anonymous. Okay, so we don't care about that. The mapping is not backed by any file. That's probably what we want to have, right? So it's going to be anonymous. Private and anonymous. But isn't private updates to the mapping are not visible to other processing mapping the same file and are not carried through the underlying file? It is unspecified with the changes made to the file. So I'm not sure if we need private or anything, so okay, flag is ignored, map fixed, no replace, grows down. I feel like this is the only two things we need to have in here. Yeah, so that's the only thing. So private and anonymous. So fd call has returned the file descriptor can be closed immediately without invalidating. The mapping is not backed by any file. The fd argument is however some implementation require fd to be -1 if anonymous or unknown is specified. So okay, so let's put -1 in here. And what about an offset? It's an offset starting from the address. I suppose it could be just 0, right? So, and here's our memory. Maybe we can call it a code, right? And so, as far as I know, this entire thing returns map failed in case of an error, right? So if code is equal to map failed, right, we have to do nob error, could not allocate executable memory because of this stupid reason, str error, error no, and let's just exit with non-zero exit code, actually just one. So let me try to compile, and it does not even compile because we don't know where to find mmap. Okay, so we have to include man, not mmap, but mman. All right, that's it. So that's basically it. So let's try to run. We'll already try to run it. As you can see, it's successfully, you know, finished right without doing anything. So the next thing we probably need to do, we need to copy all of the code into that thing, right? So we need to do sb items sb count. Is that how we use memcopy? I think that's literally how we use memcopy. I want you to do man actually. Thank you very much. Yeah, first destination, second source, and the third is the size. So we're just copying this entire thing. Then I take the code and I cast it to run function, and then I call that function. Hopefully that will perform hello world, right? So let's actually see if it's going to work. Right, so this is the count, boom, and nothing happened. Literally nothing freaking happened, which is rather interesting. So we may want to try go through the debugger and actually see. So let me do gf2 runbin, and let's do run, and what is it called? Hello. Wait, did I actually run the right thing? Yeah, I did run the right thing, so it was runbin. So I was trying to make sure that I didn't run to this thing or anything like that, so that should be fine. All right. So let me see. So we're gonna be gf2 runbin, and we're gonna break main, and so let's do run hello bin. Not b. God damn it, not bf. Run hello bin. Yeah, there we go. Do I want to? Yeah, let's go to that. So this is the file path. So let me see if we're looking into the correct file path. Yeah, it is correct file path. That is nice. So we're reading the entire file. Okay, so the code. Do we have the code? Right, the code seems to be all right. So the pointer at least, and we're copying that stuff into the code. We might as well actually, you know, take a look at the characters of the code, right, and say like, take a look at the first like 50 of those characters, right, and see. Yeah, it does look, in fact, like something. Okay, so we're about to call to this function, right? So let's actually try to do that. Okay. Doesn't it look familiar? Move for X, move for DI, move for RSI, move for DX, syscall, return. Right. Doesn't it look familiar? Because this is literally what we had in here, right? Rex, RDI, RSI, RDX. And you probably noticed something weird in there. You probably noticed something weird there. I accidentally closed this entire thing, but let me open it one more time. Right, so we're gonna break on main, right, and I'm gonna run with hello bin. Right, so let's actually go until here, and then I'm gonna go here, and I'm gonna step into that. You may notice something weird already, right? We're about to put the pointer to the data in here, into the RSI, but the pointer to the data is weird. What is it pointing into? It's not really pointing anywhere, right? So yeah, so it's relative. It is relative, and I suppose we need to do something like layer or something like that, or we could even do something cooler. What if we accept the pointer, actually the pointer and the size through the arguments? We can actually do that. We can actually do that. We can allocate some string and we can just pass it to the assembly there. So essentially, we know the call convention of C on Linux x86-84. So it's the same as the syscall convention. So RDI is the first argument, RSI is the second, RDX is the third, and so on and so forth. If we modify the function to accept a pointer, like a buffer, const, and size t size, buffer is going to be in RDI, buffer is going to be an RDI, and the size is going to be an RSI. Right, so, and essentially the thing we'll have to do, we'll have to just reshuffle some things. Anyway, so let's try to do that. So we don't even need any data in here, right? So we don't really need any data in here. And knowing how to parse the arguments that are passed to our function through C could be useful, because maybe we can put all of the memory allocation on the host C program, right? We can put it on the host C program, so it can pre-allocate some buffer, and the assembly is going to just use that buffer that we pre-allocated for it. So that's actually kind of interesting, right? So it simplifies a lot of things. So anyway, we need to move RDI into RSI, right? So we need to move it into RSI, and so this is going to be the second one. So RDI, and that actually kind of kills the whole thing. So that means we have to do that in a slightly different order. We have to move RSI into RDX, all right, and then RDI into RSI. That's what we have to do, right? So we have to sort of shift them around. Then we have to move RDI 1, and then Rex sys right, and then syscall, and then return, right? So, and that's probably going to be the thing that we can do. Right, so RSI and RDI, So we sort of like shift them around, right? So then we put RDI in here. It's kind of like a weird thing, but it is what it is. Right, so let me do FOSM, hello awesome. Yes. So that created Labin. And we need to update like the way we do all of that. Yeah, that's for sure. So even if I try to compile, it will start complaining because we don't really provide anything particularly useful in there. So we can have something like message your mom, and we can pass the message in there, and we can do a strlen message like this. So we pass this stuff in here. So the message is going to be RDI. Right, so is it going to be RDI? Where is my thingy majingy? RDI, and the size is going to be RSI. All right, so let's recompile, and everything seems to be fine. And also FOSM hello awesome. And then we're going to do runbin hello bin. First, mother flip and try. Mother flip and try, first try. Easy peasy lemon fucking squeezy. So yeah, we generated some code. And we just executed it, and it was that simple. Right, so we just map some pages. And as you can see with the debugger, it's really easy to figure out like and troubleshoot things, right? Because you can literally step through that assembly that you just generated, right? You can just do that. 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 Anyway, I'm sorry. So that's pretty cool. How are we gonna approach all of that stuff? How are we gonna be approaching all of that stuff? Now let's go back to JIT. Let's go back to JIT, and this is somewhere we're gonna start generating the assembly code. So I suppose we're gonna be generating assembly code into the string builder, right? So this is gonna be basically the code, right? Because I'm gonna be effectively appending that code. Right, so essentially we need to start iterating the OPs. So here we do an interpretation of the code. Maybe I want to actually keep that. I think interpretation of the code is valuable, so we may want to move that somewhere here. So interpret, right. I'm going to put it like that, and I'm going to grab the entirety of this entire thing. Grab the entirety of this entire thing, interpret, and I'm going to put it in here. And I'm going to just call this thing interpret like that. And I'm going to go to the compilation errors. Right. So ops, we need to accept the ops in here. So this is ops. Return 1. Suppose this thing may return like an error. So let's actually do return false, and at the end we're going to return true if everything is okay, and essentially if this thing failed, we're going to return a non-zero exit code indicating an error. Interpret accepts the ops. It accepts the ops, and there we go. Everything seems to be okie dokie a karaoke. So interestingly, we do allocate some memory that we would probably like to deallocate. So essentially, maybe I would like to do a defer section in here somewhere. Alright, where I just free the memory I allocated, so it's just the items, like so. And here we probably want to have some sort of a result, and result is going to be by default is going to be maybe false, right? And when you return false in here, you do knob return defer false, like that, and return defer actually goes to defer section, automatically frees the memory and returns the boolean, and that should be basically it. So in case of an error, right, it's going to always deallocate all of that stuff. So we have interpretation, and it seems to be working. So the next thing we need to do, we need to implement compilation. Yeah, compile, maybe JIT compile. So ops. I don't really know what exactly it is going to return. Maybe it is going to return the code actually. Yeah, so let me see. We can have a thing called code, right? So this is going to be the code, and the JIT compile is going to accept ops and return a pointer to. This is so fucking cool, isn't it cool? You give a function. Yeah, listen. You give a function a sequence of ops, and it returns you the code, right? And the code is the pointer to a function that you can just call. That's so fucking funny, actually. All right, this thing is obviously going to be null, right? We might as well actually call it like T to indicate that, you know, it's an error or something like that. Yeah, exactly. This is going to be so fucking cool. The fact that it looks like that is actually so freaking funny. Look at that. I think it's something that is going to compile, right? So code, yeah, it didn't like that I didn't put, you know. Yeah, it even compiles, like it's a syntactically and semantically correct thing. Holy shit. That is so fucking funny. Right, it just returns you that. I love it. I love it so fucking much. Holy fuck. Anyway, that is really, really funny. So, yes, sir. We need to start iterating. Well, first of all, we probably need to allocate some memory, but first we need to figure out how much memory we need. We need to collect all of that stuff, right? So nob string builder, and this is going to be the code, right? So this is going to be just that, and let's go through all of the operations, right? So let's go through all of the operations and the ops. Might as well just take all of those motherfuckers and just sort of allocate them, not really pre-allocate them, but pre-create the cases for them. So we can have op kind. Right, so I'm gonna just put the stuff in here. Opa, and might as well just remove all of these things, and let's delete trailing white spaces. I'm gonna go here, and then I'm gonna do something like that. So this is the case, and then here I can do assert to do something like that, and just put it in here. Boom. And this one, right? So we probably want to put default in here and just say something is unreachable. So something is in fact unreachable. So now we have to just generate some scheiße for all of these things. And interestingly, we need to basically have a dedicated register, dedicated register to that is going to be the head, right? It is going to be the head. Let's say it's going to be the first argument in here, RDI, right? So it's going to be the RDI. And the question is, can I do the following shit? So we already have think like hello, right? I'm probably going to do something like that. So I have RDI, move like RDI. Can I increment what's inside of RDI, but as a byte? Sorry, Tsoding, I paused you for a moment. It's okay, we're gonna wait for you. Did you unpause me already? May I continue, please? Okay, very good. Okay, so nice. Can I do shit like that? Can I do shit like that? So let's find out. Let's find out. Let's do fuzz hello asm. I can. You know what's funny? I can take individual instructions and just compile them into their pure byte form. And then I can look into their bin like this, and maybe even into the hexel mode. And here is this scheiße in the hexel mode. FE65. So FE65. Might as well even do something like this. So I'm gonna do xxd hello bin. Right. So what I can do, okay, anyway, we just need to now push that thing to the code, right? So that's going to be a single increment, right? This is going to be a single increment. But that is not enough, because inc doesn't really increment by one, it increments by an operand, right? It increments by the operand. But for now, let's actually just like do inc, right? Just to see how it's gonna go. So knob, I think da append. So we da appending 2 bytes. Where is the compilation? Fe, so this is the first byte. And then we append the second byte 07. And that is supposed to be this thing. So this is how we're going to do that. This is how we're going to do that. It would be kind of cool if we could just do something like 07. I wonder if we can do that. I think cmd append can do that. Cmd append. But you know what's funny? Well, I mean, it expects const char. Yeah, we can't really easily do that, so we're going to be doing it like that, at least for now. Right, at least for now. So what I'm thinking, actually, are we writing our own assembly? Yeah, we're basically hard-coding the machine code. We're basically hard-coding the machine code. All right. So what I want to do for now is just like generate one instruction here, right? Generate one instruction here, and maybe break out of, god damn switch, right? Go to out, right? Freaking right. So this is going to be out. And this is where I'm going to be doing the M mapping, right? So I'm gonna just steal the code from here. So this is the code, but maybe I'm gonna call it execode. Execode. Yeah, this is gonna be called execode, and this is SB. Well, you know what? Might as well call that thing SB for the sake of consistency. Right, so this is going to be SB actually. Wait a freaking second. Can you do shit like this in C? Is that something you can do in C? Because I know that I can do SB append sister. SB append. Holy shit! What the fuck? This is so cool. And now I can have like individual instructions as single lines in here. That is so awesome. What the fuck? I can even. Yo, mother flipper, yo. Mother flipper, yo. Okay, so, and the next thing we're gonna do in here, we're gonna just do mem copy. We're gonna just do mem copy. And we're simply probably gonna return la code. Alright, but on top of that, we need to free whatever we have NSB items, right? Because we don't really need that anymore. We don't really need that anymore. And so since we're going to be passing the memory, so I suppose we need to accept the memory in here, right? So that's going to be the memory. So in the interpretation, the memory is expanding. In here, the memory is going to be fixed, right? So this is something that we have to keep in mind. And we probably not going to be checking the boundaries. Maybe we can, but I don't want to spend time on that. So fuck that. So, all right, so this is a code T, and I'm gonna just be casting all of that stuff. Maybe I don't have to because it's already void star, so nobody gives a shice. All right, so let's pre-allocate some memory. We're gonna have some memory, malloc, and let's maybe allocate 10 megabytes of memory, right? So why not? So it's gonna be 10 megabytes, and we're gonna just like pass that memory in there, and boom. So is it going to compile, meine Freunde? Is this Haufenscheiße going to compile, meine Freunde? That's the $1 million question. Haufenscheiße. Alright, so we return 1, and here we supposed to... Okay, this one is interesting. So we have, in case of an error, we probably want to return null, right? So that's really funny. So we still probably want to do something like that, right? So the code, t code, right? And if code equal to null, we still want to return 1, right? But then if everything okay, we want to just do that, and somewhere here, this is where we're going to be allocating all that stuff, and maybe also freeing that memory. Look at that! Look how productive I am. Can you be that productive and efficient in JavaScript? I don't freaking think so. So Twitch is replacing X with 00. That's super gay. So that's why you like it. I knew that. I freaking knew that. So let me see. Let me see. So JIT compiled it. You can't see it in the chat. Yeah, I know what you're talking about, right? So the I've seen how it is on Twitch, and it's all right. It is gay, I do agree with that, but there's nothing wrong with that at the same time. So what? All right. So what we gonna do? I just want to try to run all of that in a debugger and see if I can see that inc byte RDI. RDI. So I wonder if it's going to work well. So beef JIT, and so it's gonna be hello BF, right? Hello BF segmentation flow. I mean, that's understandable. So this is something that I probably want to actually do in out, right? So this is something that I want to do in out. I want to do a return. So the reason why it's segfaulted is because I never return out of that, so it continued executing stuff like that, right? So we need to return out of that. Haufenscheiße. I'm really sorry. So how are we going to be doing that? So let's see, how do you even return in x86-64? It's literally a single byte C3. Looks like a small penis actually. Look at it. So yeah, C3. And let's literally append that thing at the end, right? Knob SB append sister. Append sister is going to be SB X and C3. Okay, so this is going to be C3. So if you do C3, it is going to return. It's probably not going to even big personality though. Yeah, exactly. So it's not going to segfault because it's going to return out of that function right away, hopefully. It's kind of interesting how some of the x86-64 instructions are literally like just 1 byte. Just like 1 byte. Another interesting thing about x86-64 is that NOP, you would expect that NOP is 0, right? But no, fuck you, it's 90. That's NOP. That's NOP for you. Nope. To be fair, I'm not really that proficient in the hardware design. Maybe there is a good reason for that. But personally, if I was designing things, I would make 0 a NOP. 0 is taken by something else, yeah, probably. But anyways, let's try to recompile bf JIT, and it's gonna be hello bf, and I'm gonna trust. And as you can see, it exits perfectly. It doesn't even segfault. If I don't include that thing, it segfaults. If I do include that single byte, it doesn't segfault because it actually returns from the function. Isn't that poggers, my friend? I think it is, in fact, a poggers. Anyways, so let's go ahead and just like open all of that scheisse in the debugger, so GF2, and see how it's gonna go. So I'm gonna break in the main. I'm gonna break in the main, and I'm gonna run hello BF. So what do we have in here? Can I just run up until maybe? So yeah, you can actually run up until a certain moment. Maybe skip to. Yeah, I think that's what we want to do. We want to skip to. Right. So, and I'm gonna do in here. So let's take a look at. Yeah. Okay. So that's kind of cool. It prepares the you know, the call arguments, right? So it just like does the pointer arithmetic and stuff like that, and then it pushes this stuff into RDI, and then it calls the to the function. So let's actually go ahead and just execute all of that, and we're about to call into the generated function. I forgot to recompile. Why did it segfold? Cannot access memory. What? It was working fine without any debugger. And what happened? Excuse me. Fucking. Wait a second. It's just like everything's fine. It is working fine. Like, am I going crazy or something? Yeah, I think I am. Break main run. Right, and it's just like. So what when I did run, oh, I think I just did run, but why it worked fine without requiring the argument? So that is literally bizarre. So file path, no, this is not it. File path I said. Yeah, there's no file path, but why is it still working though? This is bizarre. Yeah, this is literally bizarre. Because if I don't provide any arguments, yeah, I just exit normally. Is skip to different to run until? If I remember correctly, the instructions of Nuxt. They are, but I don't remember what's the difference. I don't fucking remember. From the description, what exactly is the difference? Anyways, so let me try to do that one more time. I think I know what the fuck is going on. So I think I'm gonna do things slightly differently. All right, so first of all, I'm gonna provide the argument, that's for sure. Then I'm gonna just create a second breakpoint, right? So that's it. And I'm gonna just continue, and that's it, right? So I think that's the easiest way for me to go. Let's actually see how it is going to call to the. It recognized it. Perfect. Perfect. My God. Oh. This is so beautiful. That is an assembly generated at runtime. So imagine you in JavaScript, you concatenated a string and you passed that string into a val. That's what basically it is, except in a real programming language on a real hardware. Not in a toy programming language and a toy virtual machine that is trying to become operating system or something like that. So this is the real proper shit. This is the real stuff. That's what it is. So it's absolutely fucking epic. Love it. I absolutely fucking love it, mind it. But this is absolute freaking bullshit. You know why? Because we're supposed to add operand in there, right? We're supposed to add operand in there. Instead of inc byte, what we have to do, if I understand correctly, we have to sort of add byte RDI and the operand. And I don't think that's the way it works, if you know what I mean. I don't think that's the way it works. We can try, and we're probably gonna miserably fail. So let me get rid of all of that stuff, and I'm gonna just like literally do add byte RDI, and I'm going to try to add 69 in there. And so let me just try to do FASM and XX. You literally can't just do that. What if I do 0 in here? Oof, 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 oof. Right, so look at that. So that's 3 bytes. First is 8007, and 0 is just 0. If you do 1, it's just 1, 2, it's just that, then 69. So basically the operand, the value that you add in there is going to be like this byte. But what if it's bigger than, you know, a single byte? How you do that? You can't do that. That is interesting, isn't it? That is interesting. So you literally can't do that. 256, 155. That makes sense. That makes a lot of sense. But how are we going to be representing that in assembly? Essentially, we can divide the operand. Yeah. x86-64 assembly is more safely typed than Rust, exactly. So this is also huge props to FASM as well. This Motherphilippa checks for all of that stuff and just reports and everything. And it's written in itself. That's what's cool about it. This thing is written in itself. Right, and it's so cool. So essentially, if we can split the operand into chunks of 255, right? We can split it into chunks of 255 and just make several of them. So that's the way we can basically do that. Another thing we can do, okay, another thing we can do, we can maybe like move byte, fuck that, we're gonna be doing it like that. Right. Ooh, if it wraps, can't we just mode? Do you know what is mode in x86-64? Well, you probably do know. I'm sorry for saying that. I think it's too much effort because mode is literally div, right? So it's literally div, and div requires very specific registers for the inputs and very specific registers. You mean in the intermediate representation? Ah, in the intermediate representation, probably. Yeah, I see what you mean. I'm sorry, I misunderstood you. Oh, okay, I see what you mean. So basically, do that in the intermediate representation. I guess mod 255. That's not a bad idea, actually. But is it going to be correct? Is it going to be correct? I'm actually, for some reason, can't verify in my head intuitively if it's going to be correct. So I'm assuming what you mean, and you mean a very interesting thing actually. In case of a plus, we just do something like that. I intuitively don't feel that it is correct, right? So I need like a hard proof that it is going to be correct, so I'm not going to be doing that for now. So you know what I'm going to do? I'm going to just do an assert. I'm going to just do an assert that operand is less than 256, and that's it. All right, so, and we can even do something like support bigger operands. So I think that's the easiest thing to do. So that's how I do shit. Yeah, that's how I do shit. Okay, good. X knob is p append, and this is going to be that. And in here, what we did, where is my awesome? We just did this thing, right? We just literally did this thing. And what we need to append in here is rather interesting. So since it's a single byte, we can literally just append you know, a thing in there which is going to be operand, right? So yeah. pretty cool. Now I'm going to just build. So nope da append. There we go. And I'm going to try to run this. Run hello bf. Yeah, let's give it break main. Run hello bf. So continue here. Look at that. Look at that. Look at that. So interestingly, by the way, we can have a memory. Can we have a memory? We should be able. God damn it. So we actually kind of lost it. So we can't really see what's in the memory. But anyway, so I'm going to say, then return out of that. We returned out of this entire thing. And yeah, so that seems to be working. So that's pretty cool. That is pretty cool. And we need to start implementing deck. So surprisingly, all of that stuff is kind of easier to implement than interpret, right? So in case of an interpret, yeah, you have to do this kind of stuff. You also need to increment IP yourself, right? You also need to increment IP yourself and everything. So left, I think it's going to be even easier for left and stuff like that, because you just basically add values to RDI and stuff like that. So all of that is going to be way easier, actually. Strangely is going to be all easier, but let's go ahead and just do that. Let's just go ahead and do that. So break. So what do we have in here? So for the break, we're going to be actually just subtracting all of that stuff. We're going to be just subtracting all of that stuff. And that one is super easy, right? So because it's just 0, yeah, it's going to be just 1. Yeah. Okay, so that's the whole implementation. JIT compilation at its core, at its essence, is so goddamn dumb. It's just like right. Sub. Well, I mean, okay, I actually cheated a little bit. I kind of use FASM as a lookup table of different instructions and stuff like that. Is it a cheating? Is it by itself a cheating? I don't really know. Maybe it is. Maybe it is not. And in here, of course, we probably want to do something like that. It's not cheating, that's being smart. Maybe, right. So because we kind of rely on the hard work that was done by the FASM developers. And the FASM developers did like enormous work to figure all of that stuff out. It's actually quite amazing. Like the FASM as a piece of software and also as a community around it it's like a small you know, pearl of like a treasure in the software development world, right? So yeah, it's absolutely beautiful. Like you don't see things like that anymore in 2024. Well, I mean, we see it in the case of flight assembly, but it's so freaking rare. Right, I love it so much. So anyway, so we have a decrement and stuff like that. So in case of the left, so essentially we are moving left and right the pointer, which is RDA. So if I want to move RDA, so what am I going to be doing? I'm going to be subtracting RDA, right? So what if I want to subtract 0 from RDA? So how is it going to look like? It's going to look kind of weird. If I'm subtracting 1, okay, 2, okay. So what if I have 255? So, oh, all right. So that expands. That is so weird. So it only changes this thing. So it's 3 bytes. Right, we probably want to have like an extended version of it. We probably have, yeah, we probably want to have an extended version of it, which allows you to actually do 4 bytes in here, right? So it allows you to do 4 bytes in here. Yeah, that's pretty cool. So 55, yeah, I can see that. So let's just like do that. Nope, SB append sister SB X X X. So this is that. So it's a sub RDA. So quite often the same mnemonic instructions, they have like actually several versions, right? So they may have a shorter version or a longer version and stuff like that. So, and because of that, they're sort of like encoded slightly differently, right? So you have to be aware of that. When you just programming in assembly as a text, you usually don't see that, right? But once you go into the low-level machine instructions, it becomes really visible and starts to matter, actually. It starts to matter. All right. So yeah, and what we have to do in here, so this one is rather interesting because we need to take the operand, right? So we need to take the operand and we have to cast it to uint32. But what's interesting is that we need to interpret it as a sequence of bytes, specifically LSB. So x86-64 is already LSB. It's already LSB. So we probably want to have something like operand in here, right? So we're going to cast it. And the thing we're going to do, we're going to take a pointer to the operand, right? And we're going to use something like nobsb append many, right? And that thing allows you to essentially provide a pointer and the size. It allows you to provide the pointer and the size and append several things in there. It's actually DA menu. That's right. Yeah, you provide the pointer to the items and the amount of items, and in here I provide the pointer to that operand, which I explicitly converted to uint32. This is very important, by the way, right? So it has to be located in that region of memory, and then I do size of operand, and that will append 4 bytes, and it's going to be LSB because x86-64 is LSB, hopefully. All right, so that's basically it. That's basically it. Does it make sense? Hopefully that makes sense. So that's the implementation. So it's funny is that I really like how like one instruction is actually a chunk of brainfuck instructions, right? So that's kind of useful, I think. And it's developing this thing was really important because we basically can copy paste implementation for the write operation, right? So it's the only thing we need to change is sub to add, right? So sub should become add. Right, so let's actually do add and see how it changes now. Yeah, it basically changes like that. It's kind of similar. Ooh, this one. Oh yeah, I see. So 255. Yeah, okay. So that's the long version of this thing. And we're gonna put that stuff in here. Right, so x nobsb append sister. What the fuck is going on? Emacs being weird a little bit. Add RDI. And we'll literally repeat that thing. We already implemented the compilation of 4 instructions. Already implemented compilation of 4 instructions. Interestingly, oof. So the input, let's actually omit input. Let's not spend time on that. I don't think it's that important actually. So the output is rather interesting. So what we want to do, we probably want to call to write syscall. We want to call to write syscall. But how are we going to go about that? RDI stores the pointer to the thing, right? It stores the pointer to the thing. But RDI in our case is supposed to be the FD. So I have an idea. What if we just like push RDI onto the stack, right? So we're kind of saving RDI. We're just saving it, right? So then I'm moving RDI into RSI, which is the second argument of write. So we move into RSI, which is correct. So then we say that RDI is going to be 1 because we're going to be writing 1 single byte, right? And on top of that, probably RDI itself has to be also 1, which is the standard output, right? Which is the standard output. And on top of that, we want to move rex and say right, which is going to be 1. And then we want to perform the syscall. So output of a single character is going to be that. It is going to be that, but it can be repeated several times. So, and I'm thinking how we're going to go about that. I'm actually copy paste that piece of code the operand amount of times. I think it's going to be easier for me for now, if that makes any sense. What's interesting is that none of that code really depends on the current value in the memory. So all of that shit could be hard-coded as one single blob, in fact. Right, so it can be hard-coded as one single blob. But I would like to separate it anyway. Right, I would like to separate it anyway. And I think another thing I forgot is to pop RDI, right? So I forgot to pop RDI. I think that's quite important, right? So we can also check for the errors in Rex, but I mean, fuck that. So let me see. So I can try to take a look at that. So it's 57. No. Yeah, so this one is gonna be push RDI, knob SB, append sister SB, and what was that? 57. 57. Okay, cool. Next thing is gonna be this stuff. Oof. Okay, that's like a full thing in here, which is understandable, I suppose. So x, 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 x. All right, so this one is going to be that. I mean, yeah, I want to just do something like that. This is not particularly convenient, like doing that one by one. Doing it one by one, it is not really convenient, honestly. Might as well maybe just copy the rest of the things, like so, and just do them like this, so it's a little bit easier for me to then simply copy paste stuff. Right, is it gonna be better? Is it gonna be better? I don't really know. Right, move RSI, RDI, so let me see what's going on in here. So this is gonna be just that. Might as well now just move on to the next thing and fix them up a little bit later. I fucked up something. Wait a second. Why there's RDI 2 times? I think I meant RDX on this one. So I'm setting sys right. Then I'm moving RDI into RSI, which is going to be the second parameter. For the RDI, for the first parameter, I put that one, and RDX is the third parameter, is going to be 1. Then I do syscall and I pop RDI back, right? So that makes sense. And this one is going to be RDX, right? So RDI is just that. And let me double check for the RDI, and that's the essentially that stuff. Okay. So that is understandable. All right. This is a different thing now. Let me double check that it is in fact different. Yeah, it is different. It's different like in here, which is kind of funny, I think. So the syscall, the syscall is funny. And then we do simply pop. And it's that. This is probably the most complicated command in all of them, I think. This is the longest sort of command. And it's probably why I don't want to go into the input as well, because it's going to be even more complicated. Because we need to figure out like where, well, I mean, yeah. Well, to be fair, input is going to be not that different from the output. I don't think it's going to be that different, actually. Yeah, I don't think it's going to be that different. I don't think it's going to be that different. Input is just sysread on the stdin. Yeah, exactly. Okay, and that's all. We're almost done, actually. Believe it or not, we're almost done. So jumping is kind of interesting. It is kind of interesting because what we have to do, we have to first check if the thing itself is 0 or not. How are we going to be checking that? Maybe we first have to read it. Right, maybe we first have to read it. So let me see. So what if I just move AL RDI? So I'm sort of reading the first byte, but I have to be careful with how I read the byte. So I want to clean up racks, right? I want to clean up racks. So, and then essentially what I want to do, if it's 0, right? So if it is 0, so what I do, I just test racks to itself and then just do JZ in that case, and that's going to be an address, actually a relative address. As far as I know, JZ jumps relatively. Right, so we can even provide some sort of a label, loop, and, well, I mean, again, let's call it again. And let's just jump there, just to trigger that specific thing. So that's basically the sequence we have to generate in here. So now, and what's funny is that for the non-zero, it's literally the same except NZ, right? And this is an interesting stuff. This is an interesting stuff because that will require backpatching. That will require backpatching. So let me now try some stuff. I want to replace some of these things with like a bunch of knobs, right? So let's say we're going to have 3 knobs. And we know that knob is 90, right? So it's actually very easy to see. So now I'm going to take a look at that. Okay, so nap, so 7. 75 FB. And here is an interesting stuff. What if I have knobs after that? By the way, we probably want to do GZ, right? So we're working with GZ. Okay. So look, 3 knobs in front, 7403, 3 knobs in front, right? But here is the thing. If I remove 1 knob, it's going to be 7402. So it's a relative jump forward. It's a relative jump forward. And if you jump backwards, it's actually negative value because it has like a, you know, significant bit set to 1. Right, but it's a very short relative jump. It's a very short relative jump. So to make it actually visible, I think we need to have a lot of knobs. Right, so let's say, okay, so this is 5 knobs. This is 10 knobs, right? So this is 10 knobs. Okay, so this is 20, 30, 40, 50, 60, 70, 80, 90, 100. Right, so this is 100 of them. And it's still a very short one, right? It is still very short one. So even though like we have 100, because it fits into a single byte, right? It just fits into a single byte. So that's kind of the problem in here. So, okay, 200. 200. Now we're talking. Now we're talking. This one is a little bit interesting. Right, so, and as far as I know, the longer version is actually allows you to take like 4 bytes in here. So here is the 4 bytes in there. We can even take that long ass shit. It's 200 actually. When 200 probably, oh no, it's actually bigger than 127 because it needs to be negative. That's why it actually switched to a longer version, right? Because it cannot be bigger than 127. So that's basically what happened. Right, so here's again, and let's actually jump forward. Let's jump forward, and we will clearly see, hopefully, clearly see, here is the jump 0f84, and this one is the positive, and this is C8, and C8 in specifically here is 200. It's 200. So that's pretty cool. So that's basically the operation that we have in here. That's the operation we're interested in. It's kind of funny that you have to do this kind of stuff to trigger like a FASM to use a different version of the instruction, like a longer one. It's really fun, actually. It's really fun. I like that. Isn't it fun? I think it's fun. Okay. So what do we have? So I would like to, so this is JZ, right? So we're definitely doing JZ, yeah. So this is in fact JZ, and I would like to just save that version, right? So I would like to just save that version. So this is JZ, right? This is JZ, and this is the relative address. But the thing is, we don't know all of these relative addresses yet. We just don't know them. We need to sort of do the first pass, then save all of the addresses of all of the operands and backpatch them. We'll need to backpatch them. So this is another interesting thing that we'll have to do. Right, so yeah, let me see. Anyway, so let me simply get rid of all of these snobs. Right, we don't really need them anymore. It's nice to know how to trigger this sort of behavior. What I'm interested in is I'm interested in these things. Zoring ZARs, then moving byte into there, then testing and stuff like that. That's what I'm interested in as of right now. Right, so that's more important things. All right, so let me now grab this thing. All right, and this is going to be just like that. I actually wanted to include semicolon, please. It's kind of difficult to include semicolon. Okay, so it means I have to do it like that. So because I just need to do it like this. Yeah, there we go, mother flipper, there we go. Where's my hello FASM? Let's take a look at the code for this thing. Okay, this one is pretty straightforward. It's just that. So this is ZOR, X, X, X. Cool. Now this is that one. That one is even shorter, and that is even cooler. X, X. Cool. Test. That's another one. Okay, so this is test. Let's align all of these things in here. So for the jump, we're only gonna do this thing, right? We're only gonna do this thing. But what we have to do? We can actually know the operand address. And the operand address is basically the count, because after that we can just add 4 empty bytes, like so. But we know the operand address. We now need to save it somewhere. We now need to save it somewhere. So let me maybe create a special type, something like backpatch. And this is going to be operand address, where the operand address is located. And it's probably going to have a target, right? So it's going to be assigned integer. So this is the maybe even offset. All right, and we probably want to have a dynamic array of those. So back patches. So a single back patch is going to be items count capacity. Right, so in here we just have back patches, like so. Like so. And so what is the offset? What is the offset? Backpack, yeah. Another interesting thing, I suppose we also need to keep track of the addresses of each and individual instruction, right? Because the instruction, they have variable length. Have you noticed that? They all have a variable length. So that means we can't just, you know, use a regular values for the addresses. What's cool about ops, about intermediate representation, is that because like they're addressed very specifically. 0 index 0 is the first instruction, 1 is the second, and so on and so forth, right? Like each index is just like one instruction because they have the same length. They have the same length. And so here they have variable length. So we need to kind of like keep track of, we need to have a mapping of like index of the OP and its corresponding address in the memory of the instruction. So yeah, that's what we need to do. That is definitely what we need to do. So on top of back patches, right? So back patches are cool, but we also need to keep track of the addresses, so to speak, right? So let me see what we can do here. Addresses. And don't we already have like a stack address? We do. So what if we transform? So we already use that thing. We already use that thing for you know, for back patches when we are generating intermediate representation. We can use the same thing for keeping track of the addresses too. So what if I just call it addresses, right? So this is basically addresses. Yeah, so when I'm compiling, JIT compile, right, so this is going to be addresses. Right, and what's interesting about that is that we can simply append nob.da append to address the current length of SB. So that means in addresses, if I access the item at 0, that's the address of the OP0, and that's the address of OP1, OP2, and so on and so forth. So that's what's cool about all of that. That is what's cool about all of that. So I need to make a small break, actually. Right, so there's a little bit of a complexity in here. I'm almost done. That's what's funny about all of this. I'm almost done, but I ran out of tea and I'm kind of like running out of steam. So I think what we're gonna do, we're gonna make a small break. I'm gonna refill my cup of tea and we're gonna push through that. All right, so because we only need to implement the last 2 instructions, right? So, and so I'm actually implementing the shit in the input. I'm supposed to be implementing that in if 0. So, but it doesn't really matter. I didn't plan to implement input anyway. Right, I didn't plan to implement it anyway, so it doesn't really matter. So what's funny is that once we implement if 0, implementing if non-zero is going to be easier, because literally the only thing we'll have to change is these 2 bytes. Right. So as soon as we implement if 0, that's basically automatically implemented if non-zero. Right, so it's just like it's pretty straightforward. And even the backpatching mechanism is probably going to be applicable to this thing as well. is probably going to be applicable to this thing. All right, so let's make a small break and all right, so on the break, people actually brought to my attention that this is a little bit of a fucky-wacky situation, right? Because it literally creates a null-terminated strings, and it's just like it's not going to basically append any of these things that are important, which brings the question: how the fuck do I even do that? Well, one of the things I can do, I can maybe do DA append and just manually compute this thing, but that's a little bit of sauce. That's a little bit of sauce. That's a little bit of sauce. So we will see how we can. Well, I mean, I need to really fix it right now. So we can find in how many places. Okay, so these are the places where we do all of that. So not that many, actually. Not that many. So what I'm thinking is that X, maybe even like this. 1, 2, 3, 4, 5, 6, 7. So there's 7 of them. Which means I can just do DA append many. That's one way to do that, right? So we're just providing that thing, and it just like hopefully works. And similarly in here, so we can clearly see that there's a 7 of them, right? So we can just do a similar thing as well in here. So DA append many. And that's gonna be the 7. The 7 gonna align this entire thing like that, and that seems to be working, I suppose. So there's not that many things in here, and this is DA append many, and we are appending 4 of them. All right, so let me see. So let me try to recompile this and see if it works or not. It doesn't even know uint. What a shame. Shame. Absolute freaking shame. So unused variable, well, that's fine. Sure. Label out is defined but never used. That's fine. Anything else? Anything else? What else? Okay, so unused variable. Yeah. So it's complaining about some scheiße that I don't freaking understand. Like, what's wrong in here? So it's here. Aha. This is because the stack, yeah. So I renamed this thing, so it's now editors. And there we go. That seems to be working. That seems to be twerking. Yo. Isn't that epic? I actually worked around that stuff. Okay. Interestingly, so this is the operand address that we need to sort of backpatch. And, where I'm going to be jumping. So the way, by the way, x86-64 works, it's actually rather interesting. So first thing it does, it reads the entire instruction. So IP, which is instruction pointer, will be pointing after JZ address. It's pointing after JZ address. Only then it executes that instruction, and basically, if the condition is met correctly, it will jump to that specific address. So the address is relative to the position after the entire instruction, because that's how it works. It first reads, decodes the instructions, right, which updates the IP, and only then it performs the side effect of the instruction, which may be setting the IP to something else. And because of that, this relative address has to be calculated according to that. So, but we still need to sort of like take it like this. And so essentially, so this has to be a jump from this instruction, right? So from this instruction to to the target instruction that is located in OP operand. Right. So that means the backpatch should store both the source and the destination, the index of the source and the destination, to correctly perform that. So let me see, backpatch. So yeah, so we have an operand address, and this address is in bytes, right? It's literally an address of that 4 bytes, which we'll have to modify. So, and then we have, you know, source index, maybe even something like OP. Maybe I'm gonna even do something like this, src OP index, right? So from where we're jumping, and then DST OP index, like where we're jumping. So it's very important to know the source and the destination, so we can compute the distance of their address in bytes, right? So we know their distance address in bytes and set to the operand address. So that's why it is important to know all of these 3 things. Right. So this is going to be backpatches. Backpatches, right? So let me find it. Okay. So let's create the backpatch. Backpatch. So BP. We already have the operand address. So this is the operand address. I'm gonna just like reassign the operand address. Then we have src OP index, and src OP index, as far as I know, is just like I, right? So that's gonna be the I. Right, so that's I. And the destination OP index is whatever we have in the operand. Right, so this is whatever we have in operand. And yeah, so we don't know their byte addresses yet. We may not know their byte addresses yet. Right, so that's why we sort of like postpone all of that, and then we're gonna compute all of that later. Okay, so and then back patches, I'm gonna do nop da append, and I'm gonna pass it like this, and there we go. So we have a bunch of back patches. So funnily enough, this is like if non-zero is the same, essentially it is in fact the same, except we have to use JNZ, right? We have to use JNZ. So let's try to figure out the JNZ stuff. So I'm gonna just remove that. So this is JNZ, and again, this is gonna be nop. It's gonna be 3 of them. It's gonna be 3 of them. And of course, it's probably going to be a short version. Yeah, it is in fact a short version. So that means we need to yeah, create this thing one more time. So this is going to be 10, and we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. So that should be enough to trigger the longer version. Yeah, and here it is. Here is the longer version, and that is 0f85. So let's put that stuff in here. 0f85, and let's compare it to whatever. Okay, so 0f84. And GNZ is 85. Okay. But apart from that, they're literally the same. Okay, so afterwards, what we have to do, the back patches. So the first thing I'm going to do, I'm going to just iterate through the back patches. Back patches is going to be count plus I. And let's literally print them. I think that's interesting. So this is going to be ZU. So the operand address. What's that operand address? Yeah, so it's going to be ZU, SRC, DST. So I, so let's put it like this. Back patches, so back patches items I, back patch BP. I'm gonna call it BP. So BP operand address might as well do something like this. BP src, BP dst. There we go. I just want to see all of them. How many of them do we have? And after that, we can just say, you know, not implemented yet, right? So to do not implemented yet. So I don't want to execute anything yet, right? So, and I'm going to just do bf JIT hello bf. All right. So this is basically the amount of back patches we have. This is the amount of back patches. So an operand is like literally in bytes, and that's what we have to modify in there. That's what we have to modify. We can even confirm that. We can even confirm that operand is a correct thing by looking at their bytes and their offsets, but I don't think it's a good idea. Anyway, so here is the thing. We know addresses, right? So we can do src address, right? So this is, we're gonna have src address, addrs items. So, and we just take the index, and that's the actual address in bytes. And we're gonna have a DST as well. So, and the thing that the jump that we need to perform is basically gonna be DST address minus src address, but it can be negative, right? So we have to keep in mind that it can be negative, and because of that, so we have to maybe do something like int 32t, right? So int 32t. So, and that is basically it, right? So this is the value of the operand, right? That's the value of the operand, and then we have an operand address. So essentially we can take the CB, SB items at that specific address, and what the fuck just happened? And mem copy into it literally that operand, the size of operand, like literally like 4 bytes there, and that's how we backpatch this entire thing. That's how we backpatch this entire thing. So I just realized that another thing I forgot is that in output, if you have several outputs, you have to do something like this, right? So op operand plus I, and yeah, let me try to do that. Yeah, so you may have several of those things. You may have several of those things. This is it, if I'm not mistaken. If I'm not mistaken. Or is it? Actually, I don't think so. Because, yeah, this is a little bit incorrect. Because we have, so sort of like the destination instruction and src instruction. The address of the src that we take is actually the beginning of that thing. So that means this src has to be +1. Yeah, because we're jumping from the next one. We're jumping from the next one. And probably because of that, we want to store not the src index, but src byte address. Yeah, that's what we want. It's been revealed to me in a dream Zozin will implement a small self-hosted C compiler. This is very unlikely because we have TCC. It's already done by somebody, so I don't know. I personally don't want to do that because it's already done. So sorry. Sorry to disappoint you. Anyway, so Yeah, so this thing has to be the byte address, but this has to be the index. So we have two measure units in here. The OP index, which is very huge, which is very granular, and byte address, which is finer, right? And a particular byte address can be in the middle of a one x86-64 instruction, so which is a little bit annoying sometimes, but it is what it is. All right, so let me try to recompile whatever we're doing in here. So I'm going to go to the compilation errors. So this is a byte address, and it is in fact here a byte address. SRC, yeah, so this is byte address. And here we have SRC OP index, but it's actually SRC byte address. And that SRC byte address is in fact after we pushed that argument in here, so it's kind of like in here. So SRC byte address, so then we have an operand and so on and so forth, and here we want to repeat the same thing. Here we kind of want to repeat the same thing. Yeah, so what's going to be the next? Yeah, operand byte address. What else do we have in here? Okay, so this one is cool. Now SRC byte address, and we do want to convert it to this one, right, for the sake of operations and everything. And operand byte address. So this is where we're gonna be. Oh boy. It would be nice to have like a very small, like a test subject, which we can inspect and everything. That would have been extremely cool. Right, so I'm going to create something like test BF, which is going to be just this. Do you guys know what is this pattern? Do you guys know what is this pattern? It's actually a very common brain fog pattern, which basically sets the current cell to 0. Right. So quite often, if you're writing and optimizing Brainf compiler, you may want to detect this pattern and replace it with a single operation that just zeroes out the current byte. Because essentially, if it's 0, it will just skip it. If it's not 0, it will just keep decrementing it until it reaches 0. Right. So it basically sets it to 0. Right, and it's like a very common pattern just to zero out this thing, and it can be implemented very efficiently. So, and as far as I know, there's a lot of patterns like that in Brainfuck, and if you know a lot of them, you can program in Brainfuck in like a higher level language. Like it looks daunting because you just don't know these patterns. As soon as you kind of know these patterns, it becomes like bearable and you can implement very complicated things. Unfortunately, I personally don't know these patterns, so I don't freaking know. So anyway, let me try to see what we can do in here. We're gonna recompile this entire thing. And so I already have. Okay, so let's try to kill that and maybe refresh some stuff. Break main. I'm gonna run test BF. Okay, so we've got that. Scheißung. I'm going to maybe do this, and I'm gonna just like run it like that. And yep, so we allocated some memory. I'm gonna go into the assembly mode, and we're gonna step a couple of times, and we're jumping into this thing. All right, so that looks interesting. So that looks like the assembly that we managed to implement. Look at that. This is the jump. Look at the address of this jump. Look at the address of this jump. It points at here. Which makes sense, I suppose. Which makes sense. Or does it? That's... No, it doesn't fucking make sense. Like, why the fuck it is like that? Okay, so let's step a couple of times. Yeah, there's something incorrect in here for sure. Aren't jumps relative? Well, I mean, this disassembly shows you absolute things. So yeah, so this is incorrect. Why the fuck it is like that? This is absolutely inca-fucking-rect. It never even reaches sub, so it just like it's... This is so fucking funny, right? So it's just like, so... Wait, what the fuck is going on? Yeah. It's absolutely dumb. Okay, so why it is like that? This is an interesting bug. Yeah, it forces it to jump to itself, and it doesn't make any freaking sense, right? It doesn't make any freaking sense. I'm glad that I tested that in the debugger, because like this kind of stuff is really hard to, you know, to catch if you have complicated programming and everything. So this is the interpreter. So compile, JIT compile. Okay, so this is a JIT compiler. So src. So this is the source, and this is the destination, and this is op operand. So an operand should point at. So it may point at a bug in the intermediate representation, but I actually don't think so. Intermediate representation seems to be working fine because the interpretation worked fine. So that means intermediate representation is just like, is okay. So there's something with the compiler itself. So as we go in here, so the destination minus src, if it's bigger, it's going to be that. So everything's fine. Let me try to print this entire thing one more time. All right, so what we have, operand byte address is going to be ZU, then src byte address is going to be ZU, and DST, actually OP index is that. BP operand byte address, BP src byte address, BP DST OP index. And in here, let's just like exit with 69. Right, so okay, I forgot a new line, of course. All right. So src, so operand byte address, it's on its 10th byte, and then src, all right, so from which, relative to which we're jumping, and then DST OP index, right? So DST OP index. All right, so that seems to be cool. And then if I do DST byte address, which is going to be ZU, which is going to be just this. So far I don't see any anomaly. What the fuck is this scheiße? DST, what? This is unacceptable, meine Freunde. What the fuck is that? Why it becomes 0? So there's something with the addresses. And address out of bounds. Is it? We can... I see. So... Because we have only 3 instructions, indices 0, 1, 3. 0, 1, 3. 0, 1, 3. Okay, that is easy to fix in my opinion. So just like do something like this. Isn't that? Yeah. So just like a fake instruction. Yeah, I think that's good. It's fake instruction. Yeah, I'm really glad that we caught that. Yeah, boy, 31. Boy, sorry. As you can see, this is the 4th hour. I'm already going fucking crazy, mate. Fucking crazy, motherfucker. Becoming a fucking crazy mother. I mean, at least it didn't. Yeah, so I already ran it and it just like exited. So everything's fine already. I can try to kill this thing and then refresh it a couple of times and then break on main and just run it. And of course, let's remove the debugger, well, not debugger, but assembler. All right, and I'm gonna continue. Boom. Eh? Oh, fuck. Fuck. Shit. Damn. Continue. Let's go here. I'm gonna step 1, and we are almost ready to jump into the function. Are you guys ready? Boom. All right. Look at that. This is address 21F. Look at that. 21F. And it jumps into 21F right into the return in case it is 0. So it is in fact correct. And it actually jumped right into the return and it returned back out of the function. Holy shit, it fucking works. What the fuck? Wait. Okay. All right, so we can try to do hello world, I guess. We can try to do. I'm a little bit scared, honestly. I'm a little bit scared, but we can try to do that. Okay, I'm gonna try to recompile this entire thing. I'm gonna kill everything in here, and I'm gonna run it on hello world. We're gonna start slowly in the debugger. Awagga. Boom. Okay. So I'm gonna just step a couple of times, go into the assembler, and boom. Right. Okay. We add into the current byte 8. So let me see. So if I take a look at the hello BF, yeah, okay. So we add in 8 in here. So that makes sense, sure. Then starts the XOR and jumping and stuff like that, and we jump into 20cc somewhere there in case of an error. Where is the 20cc? Is that even an existing? It is in fact an existing address in here, so this is actually super cool. All right, so let's continue. Holy shit. Fuck yeah! Holy fuck! I did it. It's a JIT Compiler brain fuck. Holy shit! What the fuck? This is literally an assembly generated at runtime and executed, and it fucking works. What the fuck? Holy shit! Yo! So BF JIT, hello BF, boom, motherfucker, hello world, yo, easy peasy, lemon fucking squeezy. Isn't that epic? That is absolutely freaking epic. So thank you everyone. Right, so this is so cool. I didn't expect that I'm gonna manage to do that within 4 hours, right? When I started to do like the second hour, it was kind of obvious that it's a lot of work. So I thought it's going to be more work than I expected. We still didn't implement the input though, right? So, but I mean, it's kind of easy to do that, isn't it? It's just like input is going to be the output, except the write syscall, you do the read syscall, right? And you also change the FD, and that's it. That's basically, that could be homework for the viewer. Right, so it's pretty straightforward. So the way you can take this entire thing, you can even add optimizations for different patterns, as I already said. Like for example, minus within the square brackets is going to be basically set into 0, and that could be a separate operation within intermediate representation. So yeah, so I think we need to create a repo and upload it to GitHub, right? So let's go ahead and do that. So we're gonna have some examples, right? So I'm gonna move hello BF into the examples and maybe test BF into the examples as well, right? So these are the examples. Do I want to include runbin? I think runbin is rather useful, right? I think it is in fact rather useful, so maybe I'm gonna keep it. Okay, so let's do license. It's gonna be under MIT license for everyone who's interested. README. Right, so JIT Compiler for Brainf, right? So we're gonna do quick start. In a quick start, you do console knob.c knob, then bf JIT examples hello bf. There we go, and that's basically it. So we want to git ignore some of these things, but I'm not really sure yet what exactly we want to ignore in there. So first of all, let's do git init. Let's initialize the git repo. All right, so git ignore. What do we want to ignore? We want to ignore bf JIT. So the hello stuff, all of that will go away. We don't really need that in the first place, right? So all of that can just go away. Knob and a knob old, right? So that stuff is also going away, and runbin. So yeah, there we go. So that's basically everything we want to have in here, and then just gonna do ready, set, a go. There we go. So sodium. So bf JIT readme JIT compiler for Brainf. So that was so fucking fun. I didn't expect that to be so fun. Thank you so much, Bitstream, by the way, for this idea. Right, it's not my idea to implement JIT compiler for Brainf. It was Bitstream idea. So, and I really appreciate that idea. It's a very cool idea and it was a lot of fun. Thank you so much, Bitstream. So I'm gonna push that right into the repo. So if you're interested, you can play with that stuff yourself. All right, give it a star, like, subscribe. I'm gonna copy paste it in the chat. And for people on YouTube, if they're still watching, I don't know if they're still watching because it's like almost 4 hours. It's gonna be less than 4 hours because I'm gonna cut it down and stuff like that because I edit my VODs, right? I remove the breaks and dead air and stuff like that, but still gonna be pretty long for YouTube. It's still gonna be pretty long for YouTube. So let's marvel at this beauty one more time, right? So let's marvel at this beauty one more time. A boom. Okay, so I'm in the wrong place, right? So it has to be examples. Boom. Hello, mother flipping world. All right, that's it for today. Thanks everyone who's watching right now. I really appreciate that. As you can see, I didn't try to milk this project, right? So I started this project with the sole intention to finish it fully on the stream. Well, I didn't finish it fully, like some of the operations are not implemented, but you get the idea. You can implement that yourself, right? So I implemented, and that's going to be probably one episode of this series, right? I'm not going to try to milk it. Thanks everyone for watching, and I see you all on the next recreational programming session with Mr. Azuzin. I love you. Mwah.